We're going to be talking a little bit more about finding the eigenvalues of matrices, as well as their characteristic polynomials. And then at the end, we'll get into something that will kind of preview the topic for the remainder of the week. So the next topic we'll be talking about in tomorrow and Thursday's lectures is diagonalization. So we'll start to think about that a little bit at the end of today's lecture. So we're still currently in section 5.2 of your book, which is called the characteristic equation. And I want to start by giving you a warm-up question. So please do try to do this question on your own before continuing to watch me do it. So what I want you to do is try to find all the eigenvalues of this matrix as well as their eigenvectors. And if you watched, or if you did the worksheet from yesterday, there's kind of a shortcut to finding the eigenvalues for this that I would recommend doing. So we want to find all eigenvalues of A, as well as the bases for the corresponding eigenspaces. Which is just kind of a fancy way of saying what is the set of all eigenvectors. So eigenspace is just the set of all eigenvectors, and we're just trying to find a basis for each of those eigenspaces. Okay, so before I go into going over this specific example, I just want to quickly remind you kind of what we're doing big picture, although, like I said, in this example, there actually is a shortcut. But just to kind of refresh what we were talking about last time, so remember from last time. So if you're trying to find the eigenvalues of a matrix, you know that a number lambda is an eigenvalue of a matrix A if A minus lambda I times x is equal to 0 has a non-trivial solution. Or I guess I should say non-trivial solutions. And those non-trivial solutions are going to be the corresponding eigenvectors. But what we were focusing on last time was not so much finding those eigenvectors, but just determining what the actual eigenvalues are. And so if this equation has non-trivial solutions, well, A minus lambda I is itself a matrix, right? So you can think of this as like B times x is equal to 0. And if an equation like that has non-trivial solutions, it tells you that that matrix is not invertible. So if the statement above is true, that means that A minus lambda I is not invertible. And what's kind of the fastest, easiest way to talk about whether something's invertible or not? It's the determinant. So the determinant of A minus lambda I equals 0. And so our typical method for finding the eigenvalues is finding the determinant of your matrix minus lambda times the correct size identity matrix and setting that equal to 0 and solving. So on your worksheet from yesterday, I had you do that with an upper triangular matrix. And what you should see play out in that, and if you didn't do it, I would check it out because I think it's good to understand where this comes from. But basically what ends up happening is that the diagonal entries on any upper, or actually even any lower triangular matrix, are always going to be the eigenvalues. So the eigenvalues are just going to be the diagonal entries. So I'll write that down. So what we have here, so this thing here, this is kind of your general method for finding eigenvalues. And now we're talking about a special case. So the special case is that if A is upper or lower triangular, and the example I had you do on the worksheet just showed that it was true for upper, but the same idea works out for lower triangular. Its eigenvalues are the entries on its main diagonal. So in this case, our matrix A is actually technically both upper and lower triangular. So a diagonal matrix is considered upper triangular, lower triangular. So it's definitely true in this case that the eigenvalues are just those diagonal values. So we have 2, 3, and 4 are our eigenvalues. And the reason I picked this specific example, even though we'll see that it actually works out pretty simply, is I wanted to help you kind of connect eigenvalues and eigenvectors to some stuff we were talking about earlier in the quarter with linear transformations. Okay, so in this special case, we have 3 eigenvalues. So we can say lambda 1 is equal to 2, lambda 2 is equal to 3, and lambda 3 is equal to 4. Oh, and by the way, as I write them in this order, it reminded me, on your online homework, just read carefully on the questions where they ask you for eigenvalues, because I think most of them ask you to go from biggest to smallest, and it will mark it wrong if you do it in the wrong order. So just pay attention to the way they want you to enter the eigenvalues on that. Okay, so how do we go about finding now the eigenvectors corresponding to each of these? We want to basically solve the equation that is written up here, this one. And that will tell us what values of x will make lambda have this special property. Okay, so we want to solve a minus 2i times x is equal to 0. And so in this case, if you do a minus 2i, you're going to end up with 0, 0, 0, and then 0, 1, 0, 0, 0, 2. So now we're solving that times x is equal to 0. And that's really the same thing as reducing the augmented matrix, which actually in this case there's nothing to reduce. We can just kind of look at the solutions from this. So if we look here, we see that the first column has no pivot, and so that means x1 is free, or we can say x1 is equal to x1. X2 has to be 0, right? Because this would say x2 equals 0, and then the last one, 2 times x3 has to be 0, so x3 also has to be 0. And so that tells us that our solutions are of the form x1, 0, 0. And another way of writing that would be x1 times the vector 1, 0, 0. And so that tells us that any eigenvector corresponding to this eigenvalue is going to be a multiple of 1, 0, 0. And so one way we can describe this, or what we can say is a basis for the eigenspace, we can say 1, 0, 0, which you could also write as just E1, right? Because that's the first standard basis vector for R3. And what does that look like? It's just the x-axis, right? Anything where the y and z components are both 0, x can be anything, it's the x-axis. Okay, and we'll come back to why that shouldn't be surprising in a moment. So this is maybe going to be a little boring because it's going to be very similar to the last one, but So if we do a minus 3i now times x is equal to 0, this time the matrix we get, let's see, so we're going to have 2, 0, 2, 0, 0, 0, 0, 0, and then 0, 0, 1. So in this case, So in this case, we can see that our free variable ends up being x2, right? Because that's the second column is the one that doesn't have a pivot. Whereas x1 is going to equal 0 and x3 is going to equal 0. And so for this one, I didn't realize how cramped this was going to be. So let me, it's probably a way to like lasso all of this and move it over, but I'm not that fancy. So, so in this case, we're going to get x is equal to 0, x2, 0, which is the same thing as x2 times 0, 1, 0. And then that means that our basis is going to be 0, 1, 0, or we could describe it as being E2. So maybe for the sake of not boring you, because this is going to be very similar, you might kind of imagine how this is going to go. If we do this last one, you know, what's going to get cleared out? The third column will get cleared out in this case because 4 was the entry in our bottom right corner. And so in this case, x3 is going to be the free variable. And so I'll just jump to the answer here. So the answer will be that x is equal to x3 times 0, 0, 1. And so that's going to tell us that the basis for the eigenspace is going to be 0, 0, 1, which is the same thing as E3. Okay, so why should this maybe not be surprising? Well, if you think about what eigenvalues and eigenvectors are, eigenvectors are vectors that when you multiply them with a matrix, they get scaled by a particular amount. And what are eigenvalues? Eigenvalues are the amount by which those vectors are getting scaled. So this is like a kind of a nice case. You know, usually when we're finding eigenvalues and eigenvectors, they're kind of the how do I want to say this? The vectors that you're getting are not things like E1, E2, and E3. So this is kind of a special, easy to see case, but I wanted to do it for that reason, because we can connect it to stuff we already know. So we already know, if I gave you this matrix, you know, a few weeks ago, or even like a month ago, I don't remember exactly when, you would be able to tell me, okay, this is scaling E1 by 2, it's scaling E2 by 3, and it's scaling E3 by 4. Right? This is as a linear transformation. This is a linear transformation from R3 to R3 that specifically stretches in the x direction by a certain amount, in a y direction by a certain amount, and in the z direction by a certain amount. And so we just showed that using now eigenvalues and eigenvectors. So the point of this example was that what we just found with our new kind of tools is consistent with what we already knew. So again, this is like a special case of the more general stuff that we've been doing. Okay, so let's look at another example now. So as promised, this time, so we just did an example actually, right, of finding all the eigenvalues of a 3 by 3. Last time we were just doing 2 by 2s. However, that was a diagonal matrix, which is kind of a special case. So now we're going to do one that we actually have to do a little bit more work to find the eigenvalues. So we're going to find the eigenvalues of, let's call this A. So 2, 2, 3, oops, 0, 0, 3. Okay. So how do we find eigenvalues in general? Well, going back to what we were writing down on the last page, we basically want to find the determinant of our matrix minus lambda times the identity, and we want to take that and set that equal to 0. So maybe I'll hold off on writing the equals 0. Let's actually write out what that would be. So we're doing our matrix A, and then we're subtracting lambda times the identity, and really all that's going to do is it's going to subtract lambda from each of the diagonal entries. So I'll have 2 minus lambda, 2, negative 3, 0, 0, or sorry, 0, negative lambda, 3, 0, 2, negative 1, minus lambda. So I mentioned this in the other video, but when we're taking the determinant, or when you're trying to find the eigenvalues of a 3 by 3, and so you're taking the determinant, we had a few different methods for taking the determinant, and you're going to want to use cofactor expansion. So cofactor expansion was where you choose a column or a row and you kind of go down that or across that column or row, and we'll do it with this example. You don't generally want to use that like row reduction method. So we saw that one thing that you can do is you can use row operations to make your matrix upper or lower triangular actually. And then the determinant will just be the product of the diagonal entries. The reason that you don't generally want to do this here is because you're dealing with not just numbers, but also variables. So it's just going to make things get kind of overly complicated, more complicated than they need to be. Okay, so in this example, if we're taking the determinant, easiest place to expand will probably be across the first column, right? Because we have those 2 zeros, so you want to take advantage of those. So this determinant is just going to be 2 minus lambda. So maybe just to remind you real quick, there's like this way of figuring out whether things will be positive or negative, right? It's like it alternates. So if we were expanding starting at a different number, you know, that would kind of change whether it was going to be positive or negative, but the top left entry is always positive. So we do 2 minus lambda, and then we're taking the determinant of the submatrix. So let me use some other colors here. So we're doing 2 minus lambda, and then we're taking the determinant of this matrix, the matrix you would get by crossing out that row and column. It's just been a while since we've done determinants like this. And then there's nothing else in this determinant, right? Because it would just be 0 and 0, so we don't need to do those. So what does this look like? It's 2 minus lambda times, and then the determinant of a 2 by 2 is just the diagonals multiplied and then subtract the other diagonals multiplied. So we have negative lambda times negative 1 minus lambda minus 6. And then we have, so let's leave this part factored out. So when we multiply these together, we'll get a positive lambda, then we'll get a positive lambda squared, and then we'll get minus 6. And I'm going to rewrite this in a way that will make it slightly easier to see what to do next. So lambda squared plus lambda minus 6. Okay, so what are we doing with this? We're setting this equal to 0, right? Because that's where we're trying to figure out what value of lambda would make the determinant 0. And when you have some stuff that is set equal to 0, polynomial, typically you want to factor, right? So in this case, we don't want to multiply in that 2 minus lambda. Let's leave that factored out, and then we can deal with factoring this other part. So this other part will factor as lambda minus 2 and lambda plus 3. And by the way, so if you did the worksheet from yesterday, there were a few different 2 by 2 examples, and so the first 2 of them factored, then the next 2 you had to use the quadratic formula, and that's fine. Like, as you know, once you get to the point where you're setting the determinant equal to 0, you can use whatever methods you have from algebra. It's just a polynomial set equal to 0. So there was one example on the on that worksheet where you didn't get real numbers as your answer. And so there is such a thing as complex eigenvalues. Unfortunately, I don't think we're going to have a chance to talk about them. If you want to look a little bit into that, that is in your book in section, I think, 5.5. But yeah, just kind of want to let you know that it is possible that when you get to this stage of setting the determinant equal to 0, it's possible that, you know, either it doesn't factor and you have to use some other method for solving, like the quadratic formula, or it's possible that there actually is no solution. Kind of depends on what that polynomial is that you get. But in this case, we can just set each factor equal to 0, right? So we have lambda is equal to 2, we get another lambda is equal to 2, and then we get lambda is equal to -3. And so our two eigenvalues in this case would be lambda 1 is equal to 2, and our second one would be lambda 2 is equal to -3. So there's one more important thing I just want to mention about these, because this will come up in the next section. So if you remember from polynomials in like pre-calculus, there's this idea called multiplicity. And so the multiplicity of a 0 is the number of times that that 0 appears when you're solving. So whereas lambda equals -3, that only came from this one factor of lambda plus 3, whereas the lambda equals 2 came from two different factors. And so we would say that this eigenvalue has a multiplicity of 2, and this eigenvalue has a multiplicity of 1. Okay, so I put like one example like this on your homework. For the most part, it's actually kind of hard to come up with 3x3 matrices that actually work out nicely in factor like this. So, you know, usually when you're doing these problems, you'll be given a matrix that is pretty nice to start with. You know, it had a lot of zeros that work to our advantage. And then the other case that you'll maybe see is upper or lower triangular matrices, because those ones, to find the eigenvalues, all you have to do is look at the diagonal entries. Okay, so there's one more thing I wanted to mention about the characteristic polynomial that I told you last time, but I wanted to give you a little bit of like, not quite a proof, but just a little bit more justification for something. So one thing we talked about last time is that if A is a, say n by n matrix, its characteristic polynomial so the characteristic polynomial is just the determinant of a minus lambda I. Doesn't look like a polynomial, but once you actually work it out, it comes out to be a polynomial. But what's the point of what I'm writing down here is that it has degree n. So we've seen that to be true. You know, if you looked at like all the examples we did last time, those were all quadratic, and we were working with 2x2 matrices. Today we just did an example where it was a 3x3 and it came out to be cubic, degree 3. So I just want to give you a little bit of justification for why this is. I mean, so I guess the first thing I would say is if you have a diagonal matrix, it should be pretty clear why it is. So like looking at the example from the worksheet yesterday with the, or sorry, not diagonal, but upper or lower triangular. Looking at the example from yesterday, you could see that you would get like a factor from each entry on the diagonal, and that, so each entry on the diagonal contributes 1 to the degree. But it works out for any matrix. So I just want to write out kind of generally speaking what it would look like for a 2x2 and 3x3 case to justify why it is that these end up being the degree that they are. So if you have a 2x2 matrix A, B, C, D, well then the determinant of A minus lambda I is going to be the determinant of A minus lambda B, C, D minus lambda. And the way that determinants work for 2x2s, you're going to multiply A minus lambda d minus lambda, and then you're going to subtract bc. So without even multiplying this out, you can see that, what is the highest power of lambda that you could possibly get out of this? It's 2, right? Because you have lambda times another lambda, so this is going to be degree 2. So if you have a 3 by 3, so this time let's do A, B, C, D, E, F, G, H, I. Now the determinant of A minus lambda I is going to look like this. So A minus lambda, B, C, D, E minus lambda, F, G, H, and I minus lambda. So let's just say you expanded along the first row. It won't make a difference in how how the degree comes out. So if we expand along the first row, we're going to have A minus lambda times the determinant of the remaining submatrix, so E minus lambda, F, H, I minus lambda. And actually, sorry, I'm going to start over and give myself more space here because I ran out of space when I was writing this in my notes, and I meant to leave more space here. Okay, so A minus lambda times the determinant E minus lambda, F, H, I minus lambda, and then we would have minus B times the determinant of the remaining entries there, so that would be D, F, G, and I minus lambda, and then we would have plus C times the determinant of D, E minus lambda, G, H. Okay, so without even multiplying, I don't want to actually even go further with this, because right now we actually have enough information to figure out what this degree is. So we know based on the last one that when you take the determinant of a 2 by 2, you're going to get degree 2, right? Like this. So if you look at just this part, that's going to contribute degree of 2. So if you look at this entire thing, this is going to be degree 3. The highest power of lambda we'll see is 3 because you're going to have lambda squared coming from the determinant, and then you'll have the A minus lambda contributing another lambda. And that's actually like just what happened in the 3 by 3 example that we did earlier. And then if you look at these remaining pieces, these are both going to actually just be degree 1, right? Because there's only one lambda in each of them. So no matter what those numbers are, it's still just going to be degree 1. And so that tells us that overall, the highest degree that we're going to get of the whole thing, or the highest power we're going to get of everything, is going to be degree 3. So if you were to go to a bigger matrix, basically the same kind of thing would play out. And so I'm not going to go through this because it's kind of beyond what we do in this class, but there's a mathematical proof method called induction that would work really well in proving something like this. So the idea would be, well, in a 4 by 4, we've already shown that for a 3 by 3 it works. So you can kind of do this like nesting idea where if you have something that's true in smaller cases, it can kind of build into also being true for bigger cases. Yeah, I think you are probably convinced, hopefully, after seeing the 2 by 2 and the 3 by 3, and maybe you can imagine how it would go with the 4 by 4. It would look pretty similar. Okay, so there's one last thing I want to talk about today that, like I said, will be kind of a preview of what we're going to look at tomorrow. So I want to talk about something called similar matrices. So a matrix A is called similar to a matrix B if there exists a third matrix that has to be invertible, P, such that you can write A as P times B times P inverse. So this might look a little familiar to you because of a homework question I gave you a while back where you had this diagonal matrix in the middle and you kind of saw how that worked for taking different powers of A. And that's exactly what we'll get into tomorrow. So one special case of this idea happens when the matrix B that you have in the middle is a diagonal matrix. But this concept of being similar is bigger than that. It can be really any two matrices A and B that satisfy this are going to be called similar. So just to show you an example, and so this one will be an example with a diagonal matrix, just because those are kind of the easiest ones to cook up. But so this is a matrix that you had on your worksheet yesterday. So this matrix is similar to the following matrix: 9, 0, 0, negative 5. Because if you pick the matrix P is equal to 1, 1, negative 1, 1, then the inverse of that is going to be 1/2, 1/2, negative 1/2, 1/2. And I'm not going to multiply this out to verify it, but you're welcome to check yourself. If you multiply together, so P, so what needs to happen in order for them to be similar? It needs to be like this. And so if you were to write that matrix P, 1, negative 1, 1, 1, and that matrix B, 9, 0, 0, negative 5, and this inverse matrix, if you multiply these three matrices together, you will get 2, 7, 7, 2, which is what we started with. So I'm not going to do it on screen, but I would encourage you to try it yourself to convince yourself that it's true. And so because this relationship exists, we can say that the matrix A is similar to the matrix B. Now, I'm not telling you how did I come up with all these matrices? Well, that's what we'll get to tomorrow, but I just wanted to introduce the concept to you. And then there's one important fact that, again, we'll see a little bit more with tomorrow that I just wanted to mention, which is that if A and B are similar matrices, they have the same eigenvalues. And those same eigenvalues have the same multiplicities. So whatever if you list out all the eigenvalues of one, including what are the multiplicities, then that will be the same for the other one. So I wanted to prove that for you because it's kind of a nice proof. It's just like a kind of matrix algebra proof, but it uses some different stuff that we've talked about in terms of like how multiplying matrices work. So I just wanted to show that to you. I'm going to switch colors because I feel like this is getting a little boring. Let's do green. Okay, so let's say that we know that A and B are similar. That would mean that A can be written as P times B times P inverse. So if we wanted to talk about the eigenvalues, that would probably mean that we want to be taking the determinant of A minus lambda I, right? So what we're going to do is we're going to take this equation and we're going to kind of manipulate it so that we're going to end up with the determinant of A minus lambda I on one side, and then we'll see that on the other side, we'll be able to show that it's the same thing as the determinant of B minus lambda I. And therefore, we'll be able to say that they have the same characteristic equation or characteristic polynomial, and then that will suggest that they have actually the same eigenvalues. Okay, so we're going to start with this equation, and we're going to start by just subtracting lambda times the identity from both sides, which you're allowed to do, right? You can, just like with regular equations, with matrix equations, you can always subtract the same matrix from both sides. So important to remember, by the way, like, maybe let me just quickly write one thing that doesn't make sense. It would not make sense for me to ever write something like this, A minus lambda. That's kind of meaningless, right? A is a matrix, and lambda is a number. So this will come up a little bit later in this proof, but if you, like, basically if you want to kind of capture this idea of subtracting a number from a matrix, you have to do A minus lambda I. And we're familiar with that because that's what we've been doing to find the eigenvalues, but I just wanted to quickly mention that. But I think I'm going to, maybe I'll just erase it. Okay. So now we're going to do some matrix algebra kind of trickery. So I'm going to leave this left-hand side alone, and we're just going to work on the right-hand side and figure out some clever ways to rewrite some stuff. So we'll leave this part the same. But another way of writing the identity matrix is we can write it as P times P inverse, right? Because any matrix times its inverse gives you the identity. So now that we've written it like this, now we can start factoring some stuff out. And so we have to be careful here. Remember that matrix multiplication is not commutative. So for example, we would not be allowed to factor out P inverse from both of them. Because the P inverse is on the right side, we can only factor it out on the right. So what we're going to do is we're going to factor out P. And I actually did what something I said, never mind, actually, forget it. I didn't make a mistake. I thought I did for a second, but I did not. Okay, so we're factoring out P, and so we're left with B times P inverse. And then, so I guess there's one thing that I kind of am glossing over here, which is that even though lambda and, how do I want to say this? So, okay, so lambda times a number times a matrix, that does commute. So something that we talked about in the past is that if you have like K times a matrix A times another matrix B, you're allowed to do it in whatever order you want. You can do like A times K times B, or you can do A times B and then multiply it by K. As long as you're just multiplying by a number, it doesn't matter what order you're doing that, as long as the two matrices stay in the right order. So in this case, we are allowed to factor out this P and just be left with lambda times P inverse. Because lambda is a number, it doesn't matter kind of what order you put it in. So that part can be swapped around. Okay, so now we're going to factor out P inverse on the right-hand side. So we have to factor it out on the right-hand side just because, like we said, matrix multiplication, the order does matter. So when we factor it out on the right-hand side, we're going to be left with the following, and I'll explain. So the B part, I think, is clear, right? So you're factoring out from B times P inverse. Why does this become lambda I? Well, because again, you can't just have lambda. It wouldn't make sense to have a matrix minus a number. So when we're factoring out the P inverse, we have to, in order to kind of make this make sense, we need to leave it as lambda times the identity matrix. Okay, so now we're pretty much ready to start taking determinants. So what do we have now? I'm going to kind of rewrite what we had above. So now we know that A minus lambda I is the same as all this stuff. So that means that the determinants should be the same, right? So the determinant of A minus lambda I should be the same as the determinant of P times B minus lambda I times P inverse. So what have we learned about determinants? They're multiplicative, meaning that we can, if you have the determinant of two matrices multiplied together, you can separate that multiplication out. So we can write this instead as the determinant of P times the determinant of B minus lambda I times the determinant of P inverse. So now we just have numbers, right? When you have determinant, that means you're just multiplying numbers together. So we have some number, that's the determinant of P, times some number, that's the determinant of B minus lambda I, and then times another number, which is the determinant of P inverse. So now that we're just dealing with numbers, now we can switch the order that we're multiplying stuff, right? Because now we're not talking about matrices, we're just talking about numbers. So we can, for example, and it doesn't really matter to change the order, but it'll just make it a little easier to see what's going on here. So if you think back to what we talked about with the determinant of a matrix and its inverse, the product of the determinants of the matrix and its inverse, that's always going to be equal to 1. And so what are we left with? We're left with the determinant of B minus lambda I. So we started with the determinant of A minus lambda I, and we did some stuff on the right side and arrived to the conclusion that that's the same as the determinant of B minus lambda I. And how did it work? I mean, basically, maybe to summarize what we did some matrix algebra, and then when we took determinants, taking determinants allowed us to then do some stuff that we that you can't do with matrices, but that you can do with numbers, basically. And so if the determinants are the same for both, that suggests that the that A and B have the same eigenvalues, basically, because each of the things that are boxed in orange right now, those are the characteristic polynomials, right? So that suggests that A and B have the same eigenvalues. And so this will play a big role in what we're going to do tomorrow with a kind of special example of this idea. And then just to show you one thing, so going back, or maybe it was here. Yes. So going back to the first example we did, if you look on your worksheet that you did for last time, you had to find the eigenvalues of this matrix 2, 7, 7, 2, and the eigenvalues were 9 and -5. And so if you look at the matrix B that I said it's similar to, well, remember that the eigenvalues of a diagonal matrix are just the entries on the diagonal. So for this matrix as well, it's true that the eigenvalues are 9 and -5. And again, that's not a coincidence, that's always going to be true. And then we'll see tomorrow that that's actually exactly how you come up with this similar matrix B. All right, so again, I will post a worksheet for today that will just do a little bit of practice with this stuff, and then tomorrow and the following day, like I said, we'll do diagonalization, and that's going to be the last topic of the quarter. So stay tuned. I will be posting the review, and then also kind of a survey to let you tell me which questions from the review you might want to see gone over. And what I'm going to do is make a video that I'll post probably Friday, possibly Saturday, where I just go over some of the questions that people were interested in. And then additionally, and I'll send out an email about this, I'm planning to change my office hours so that they're over the weekend instead of on Thursday, just because I think that might be a slightly more useful time for you as you're doing your homework and preparing for the final. All right, thank you again for all your hard work, and just let me know if you have any questions, and I will see you next time.